Hi all. Today's topic is with respect to SDV verification validation. By now we might have understood that SDV is basically a new way of deploying code on the automotive vehicle. So because of which there are new verification validation techniques which are coming up out there so that it is developer friendly and people are able to develop the applications going forward without the hardware. So the reason why this is necessary is, say there is a third party developer and he wants to develop an application for an automotive use case. So in that case, he has to be able to deploy that application, develop that application entirely on his PC without depending on the vehicle as such. And once everything is done, maybe he can deploy it on the vehicle and he can test it out. So for that reason, going forward in the future, maybe 5 years down the line, the hardware and software will be decoupled to such an extent that the applications can be built on your laptop and you can do the entire testing and you can maybe able to deploy it in the car directly. So for doing that, there are some specific what to say validation and verification techniques which are coming up nowadays, which makes it easier for the third party developers. So recently, Covesa has published a white paper along in collaboration with the other companies, which include Bosch, ETAS, Digital Auto, and many other companies, ANSYS, and many such companies. I will anyways give the description of this. I'll anyways give the link of this white paper in the description of this video. Please do have a look. You'll get an idea with respect to that. It's an interesting and short paper to read. So here they have explained about the use case where a vehicle goes from point A to point B and the vehicle is having low charge. So the third party application, whichever has been developed, has an optimization algorithm. So it is the power optimization algorithm. So a thing is like the person has to go from point A to point B. He is having 30% charge. He is having his HVAC systems turned on, he has his infotainment system turned on, and he has his interior lighting turned on. So how does the optimization algorithm kick in so that it conserves power by cutting down or reducing the amount of power consumption by the non-essential modules like your infotainment system, like your interior lighting, and like your HVAC systems. So this is one small image which you will find in the paper. Please to read this. You will anyways see that the extra range which the optimization algorithm is gaining by switching on or switching off your the modes, because of which it is able to conserve power so that the driver can reach the destination. So here they have broken down the entire development cycle into three phases. One is a virtual prototyping, second one is a hardware integration, third one is the production. So here we will go to the first part, which is virtual prototype. So in virtual prototype, it is subcategorized into two more parts. So the first part is playground by Digital Auto, and the second one is by a simulation on ANSYS. So what do you mean by this playground? I'll just show you a small video with respect to what the playground digital auto is all about. But you can loosely relate it to your Android Studio. So if at all you would have seen in app development on Android Studio. In Android Studio, basically you can develop applications for your Android device where you can basically choose which operating system of which version of Android it is. You can just take a mock device of whatever Android phone you're targeting at, and you can mock most of these signal parameters and you can develop your application. And once it is done, you plug in your your Android phone to the Android Studio computer and then deploy the .apk file onto your device, and then you can start and you can test it. So very in those similar lines, there is this playground which is loosely linked with respect to Android Studio, but it has the same feel where these signal standards which these guys have taken are from the Covesa signal standards. And here basically, let me show you a demo. So that is the first application development. Post the application is developed, there is a physical model of the car where many of the internal workings of this car are basically mocked by some models. So these models are basically ANSYS models, which simulate the physics, electronics, and electromagnetic behavior of this particular modules. What I mean is, say there is a battery management system. So if at all there is any sharp increase in the power consumption, there will be heat dissipated by the battery pack. So something like that will be simulated in the ANSYS simulations, which cannot be seen or felt in the normal playground simulation, because in playground you can suddenly increase the power and you can write your algorithm, but in reality that might have some adverse effect on the battery pack. Or say that if at all there is a system where it says that the vehicle is at 100 kilometers per hour, and within a second or so the vehicle comes brakes to 0 kilometers per hour. So that makes no sense unless it hits a wall or something. Okay, so these kind of simulations can be, this kind of code can be written in the playground, but you will actually feel the impact of it only when you do the answer simulation. So that's the reason why you will have a playground to write your code. You can have a verification in the first level, and the second level you can use answer simulation to see whether such behavior is impacting any other system over there. So this is the answer simulation which I am talking about, where they are basically mocking the various modules inside the vehicle. So let me just show you a small demo with respect to the playground. So this is the playground application of digital.io. I will share the link in the description where they have talked about many use cases. And I have picked the EV power optimization use case, which they have basically showcased, where they spoke about in the paper. So this is the use case where if at all you see, they are explaining what the use case is all about, and now they even speak with respect to the code. So these are the various API signals which are available in the car, which are exposed for third-party developers to use them. And the API which is basically used is this specific API, which is over here, which we have used over here. And post that we are, so this is the dashboard with respect to how the vehicle behavior is another thing. I will anyways come back to this. And if at all you go back to the code, once you have tested your vehicle, once you have tested your application, once everything is done, basically you can hit deploy, and you can deploy this particular code in your virtual machine or dreamkit or express or your pilot fleet. So as nothing is connected to the system, anyways it will show an exclamation mark saying that it is not there, but they are trying to develop it so that it is deeply integrated with any of these particular modes which you want to deploy. So coming back, so here is our vehicle. It has to go from point A to point B, and I will run this application which they spoke about. So I just hit run. Okay, fine. So you can see that initially the charge of the battery is 30%, and this is the distance. Car has started moving. We can see that the vehicle intensity is 50, and you can see that the hatchback is completely turned on. And yeah, initially the infotainment system was on, but once it hits the optimization, the infotainment system has turned off, and you can still see that the vehicle intensity, the ride intensity is 50, but you see that the intensity of the HVAC has reduced, so it is consuming less power and it is conserving, and it will take some time. The car has is about to reach its destination. It is halfway through. So this is the various optimization levels. So there is level one, level two. Prior to level one, there is another level. I don't remember. You can just hit refresh and you can have a look. So here you can see that the vehicle intensity also dropped from 50 to 10. So the optimization algorithm basically has reduced the light intensity also to consume more amount of energy. And you can see that the vehicle has almost approached its destination, which is B. Now coming back to the presentation. Now once we are satisfied with respect to our testing, both in the prototype and on the answer simulation. It is time for us to deploy this particular algorithm on the kit. So here the playground guys, they have their own hardware kit, SDV enabled hardware open source kit which they are developing, which is called as Brain Kit. So where they are basically mocking the ECUs and they're mocking the campus and they're mocking many things out there on the real hardware. It's not the production vehicle, but it is the automotive grade open source hardware which they're providing. So this is what they have done. So this is the playground. This is the answer simulation. Once everything is fine, you basically deploy the code on the mock HPC. So the mock HPC has, I mean, the DreamKit's HPC. So the DreamKit HPC is connected to a zonal controller and it has an ECU. It is connected to two ECUs, one for tenant, one for the HVAC system and the lighting system. And as the battery pack is bit heavy, basically they are relying on the ANSYS battery pack simulation because it is tough to, I mean, like it is bit a heavier module. And once this hardware implementation, everything is done, everything is working correctly, then the developer can basically target the actual hardware, whatever the vehicle could be. It could be Hyundai, Toyota, or whatever it is. As long as they are following the COVID standards, and as long as they are exposing those signals. So these are the various techniques which are being created for SDV verification and validation. Please do have a look at the paper. It is really interesting. It's a very short read, and this is just an overview so that you can get an idea with respect to what you can expect by reading that paper. Thanks a lot. Thanks for your time.